Hello everybody, today we will talk a bit about remote attestation, which is a technology that is becoming more and more available in different hardware and form factors. And it's starting to show up in network protocols too, and therefore trickling into the wider internet. As always, when a new technology comes to the fore, with new principles, new actors, and starts integrating with the pre-existing deployments, there are engineering, certainly, but also societal aspects to consider and new challenges to address. We will present in this talk a practical approach that we are experimenting with in our projects, which we think can minimize the risks associated with integrating attestation into our software and network architectures, risks that are both societal and technical, while at the same time maximizing the utility of what we think is a very powerful and very useful building block. The approach that we present is one that pulls together three major constituents: open standards, open source, and formal verification methods. So Ionut, myself, and Hannes have put together the material of this presentation based on our experience and reflection on our practices. The three of us tend to tinker on open source code and open standard specifications, so you'll probably get a whiff of that. We have a number of projects in common that use attestation in one form or another. We have Verizon, Parsec, attesttls, and many more. There's always more. That's the introduction. Let's move on with the actual presentation. Okay, so to set the context, we have assembled this timeline, which provides a sort of history of attestation, certainly partial and incomplete. We wanted to try and understand where we are and how we got here. So this slide highlights a few selected landmarks, but I won't be able to go through them in detail because there's simply not enough time. But in summary, one can identify four distinct epochs. The 80s of the last century, where seminal research happens, and that takes 15 years roughly to be picked up by the industry. Then the 2000s, where attestation is driven mostly by trusted computing use cases. And it's centered on the use of TPMs as the root of trust for reporting. Then the 2010s, where attestation is driven by confidential computing use cases, now with new hardware architectures that natively provide their own RTRs. And finally, the 2020s, that's where we are now, and we see attestation becoming more and more mature. We see the emergence of standardization in network protocols and as well as in system interfaces, which is a clear sign of coming of age. So attestation is increasingly available and increasingly used, and we posit we are currently at an inflection point. So confidential computing is an awesome use case, but it's not the only one, and Dave Thaler has this nice catchphrase that says every authentication use case is also an attestation use case. And effectively, each time one has an authentication need, attestation, which is at its core a very strong form of identification, can be used instead, right, as a replacement or to reinforce the existing authentication mechanism. And so, you have use cases with enrollment protocols, TCP remediation protocols, and device attestation too is also starting to crop up. So since attestation is going to become more and more pervasive, we need to start thinking about what are the implications of that when building our solutions, and a couple of things to consider when thinking about integrating attestation into your flows are centralization and privacy. And I think it's useful to always keep those things in mind to make conscious decisions. So let's look at centralization first. So if you recall the RATS architecture, the verifier is central there, and the verification of attestation is basically the choke point in the architecture from a message flow perspective. So there's another box connected to the verifier, which is the verifier owner, which is the guy that sets the appraisal policy for evidence, and therefore is the guy that has power to decide which TCBs can be trusted, which specific combinations of hardware, firmware, software are approved to interact with your relying parties. And so it's basically the arbiter of communication. So from this perspective, the verifier is in itself a political role because controlling the verifier is crucial from a power point of view, right? Therefore, there's going to be a tussle which is inevitable over that. Now, RATS has made a pretty decent architecture in this regards that separates roles alongside tussle boundaries. So the roles can be reorganized in different ways, but still the risk of centralization is quite substantial, and if you're not really careful, you can end up in creating monopolistic situations. So one needs to think carefully about how roles and entities are mapped in their architecture, and while in some cases it's going to be possible to move the verifier and verifier owner roles under control of the user, in other cases it's not, because user and verifier have a conflict of interest of some sort. So one way to diffuse this tussle, in general, is to make sure that the verifier is neutral, completely disentangled from any specific vendor. Another way would be to decouple platform appraisal from workload appraisal, moving the latter under user control. But also in general, try to use open and standard APIs to avoid stickiness, so they can replace the actors as needed. So these are some of the things in the toolbox, and which I suggest you really think hard about. And Way, if you've not heard of Way, I suggest you go and check it. But Way is a cautionary tale in that it embodies basically all the risks that attestation brings about in a completely vertical integrated architecture. And it's been harshly criticized and eventually was retired, but it's there for you. The documentation is there for you to see and to see how not to do it. Privacy is the other big thing. So in the RATS architecture, the verifier is the only role that is allowed to see all of the evidence reported by the attester, including any PII. So if you care about the privacy of your application and users, as you should, there are at least a couple of techniques, a couple of ways to do that, which can be, by the way, combined. One is to reduce the PII that you move around simply by using claim reduction or selective disclosure techniques, or also using privacy-friendly topologies like passport mode with, say, 1-bit attestation results or multi-bit attestation results, LR4C, instead of doing the background checks where the RP is basically allowed to see everything. And the second axis is anonymity set inflation. So you hide your attester within a bigger population, and you can do that using anonymous attestation crypto primitives like DAA and variants like ECDAA, APID, whatnot, or using group identities and keys. This is the approach that FIDO2 took, and the privacy-friendly modes of PSA and ARM-CCA allow as well. Up to this point, we have seen a number of experimental sort of ad hoc designs to bring together attestation and existing security protocols, and that's of course very good if you look at the thing from an evolutionary point of view, because it shows that the fabric is bubbly, and that's an excellent health indicator. But we think we need to make a change of pace, and that the industry must come together and approach the design and implementation space in a more rigorous and standardized way. And this is where I hand over to Ionut, who will describe this approach that we have taken, mixing open source, open standards, and formal verification for getting there, for achieving this goal. Ionut?
Thank you, Thomas. So a healthy and functioning internet is an interoperable internet for which we need open and widely accepted and implemented standards. And we think there's no better place for developing these standards than the IETF. I'll start by highlighting some of the principles which make the IETF a suitable venue for this work, and then I'll give an overview of the efforts underway around attestation in IETF. First, let's go over some of the IETF principles that are meant to empower a healthy internet. First off, there's openness or open process, which states that any person that's interested should be able to have access to the work that's been going on in the IETF and to have their voice heard around any of the topics that are being discussed. The second is technical expertise or technical competence, meaning that the IETF should only produce documents on topics that it has the competence to speak to, and it strives towards sound network engineering principles in general. The third is a practical ethos of a rough consensus and running code, meaning that all the standards are based on combined engineering judgment and real-world experience of all those involved, and that more pragmatically all the documents come accompanied by a prototype in the form of code. Let's look at where remote attestation is being discussed in the IETF. So remote attestation as a topic has been slowly ramping up in the last few years, and the conceptual data flow diagram that you see here is part of the architecture document for remote attestation procedures that was published last year. The diagram shows the various roles inherent in the attestation process, and the RATS working group is actually tasked with standardizing the various mechanisms, relationships, and data formats inherent in the diagram. However, if we want to make remote attestation usable, we need to go beyond this diagram and beyond the RATS working group in general. If we want to use remote attestation for authentication, then we need to look at places where the attester and their relying party might be communicating over some other protocol. So whether this is OAuth or EST or TLS, the widespread use of this mechanism requires us to clearly define the inter-protocol workings in a way that allows as many use cases as possible. So let's go over a few examples. The first off is credential issuance or X509 certificate issuance, more precisely in this slide. So looking at EST and CMP, which are two critical components of public key infrastructure that allow an end entity to request an X509 certificate from a registration or certification authority. Remote attestation comes in to fulfill a recent requirement stated by the CA browser forum that demands stronger security guarantees for the security of the certified key pair. So the exchange is kicked off by the verifier, which sends over a nonce through the relying party to the end entity. This nonce is carried over, conveyed over in CMP or EST in a way that is defined in the document that you see highlighted above. The end entity then uses that nonce to create attestation evidence, and then packages that attestation evidence in a CSR in the way that is defined in the draft identified below. The way this draft works essentially allows the end entity to use whatever data format and whatever root of trust it has available, regardless of whether, for example, these data formats are being defined by different organizations, such as the TCG. If we move over to look at AGME, we can see that the diagram and the flow in general is pretty much identical, with some slight differences in the way that the attestation evidence is encapsulated, but still keeping the very high degree of flexibility. A similar case is presented for OAuth 2.0 clients wishing to get credentials from an authorization server. Again, the data flow is pretty much identical to that for X509 certificates. Switching over to secure channel establishment protocols, of which TLS is a primary example, we can see that the diagram is quite different, and this reflects a change in the symmetry and flexibility of these protocols compared to credential issuance, which we try to maintain in our designs as well. So in TLS, for example, both the server and the client can use remote attestation to authenticate themselves, and both of them can use remote attestation either as a substitute for public key infrastructure or alongside public key infrastructure. You might be wondering what security relevant precautions we take, given that we're working in such a sensitive context of authentication. Of course, we use our knowledge and our experience with these protocols to iron out any pitfalls, but we can't really rely just on that. And we can't even rely only on tests to perform a comprehensive check of our designs. And this is where formal verification steps in to address at least part of this gap by essentially proving that at least some of the security properties that we're interested in are upheld by our design. We use formal methods to address the soundness, and this has been quite common in the IETF more recently, for example in the work leading up to TLS 1.3 or the MLS specification. We're hoping to address these problems, and we hope for support from both industry and academia, and in some cases we've already started formally modeling our designs. So please join us both in the IETF and in the CCC, for example in the IETF Hackathon or the CCC Attestation SIG